it's common that we are interested in fitting some sort of a line, whether it be a straight line or whether it be some sort of a curved line, through paired data. And what we're looking for here is going to be one that has some best statistical validity to it. So let's first talk about the generality here, and then we'll get into some details on how we're going to do that. The somewhat traditional least squares line and what goes on behind the scenes when you hit the button on a lot of these software tools that do a lot of this for you. And we'll start with two different joint random variables, where we're going to select the one that's on the x-axis to be the one that we think might be an explanatory variable for our response quantity. Now, you could just randomly select your x and your y, which one you're going to put on which axis, but the interpretation of what you end up with is going to depend upon how you do that selection, or whether you have a valid approach or not, because this explanatory variable is sometimes also called the causal variable. That you're thinking that somehow the response is explained by or caused by this other random variable. So yes, we can indeterminately or indiscriminately switch these two, but that doesn't mean we have an appropriate relationship here. Now, from a big picture standpoint of probability, what we really want between these two is the joint density function. That's usually not an easy thing to gather or estimate, so what we oftentimes do is get the conditional distribution of our response variable and then multiply by our marginal distribution. Now, in general, what we're going to end up with here is that for, say, a specific value of x, then we're going to end up with this conditional view with a scatter that we'll represent here as a normal distribution around that central value. That central value, of course, being the conditional mean. And so this variation that we end up with is our conditional variation. And if we go and look at another location, then in general we'll have some sort of expression that relates the conditional mean, and also in principle you might end up with a function that's associated with the conditional variation. All right, so let's write that down out here to the side, that in general both of these are functions. That's in general. Now, the typical assumptions that we employ in these regression models are that first, our conditional mean will be of a straight line form. All right, so this would make this linear regression if we're doing it this way, and then that we have a constant scatter about that, meaning that's invariant with respect to x. Right, now, it's not all that complicated and difficult to expand this to some sort of nonlinear form, whether that be a parabola, maybe an exponential type of expression. A lot of those can be transformed into some equivalent linear expression, and we'll see that later on in this sequence of two modules about how we can potentially do that. So it still comes back to this linear model idea. Now, this one here we tend not to relax, because this is going to end up being essentially what we call the error. And it's the error because a specific value of y might be up in here, and that's an error with what the predictor model is going to give us, the blue line, this one given here by the conditional mean, or this one here by math. Okay, and so we're going to tend to look at that, and we'll talk about that in more detail, of how do we handle this notion of constant variation, and what does error mean, what do residuals mean, and all those sorts of things as we do the next step of developing least squares models.